Hi, welcome back to another video. Today I have a little bit of a different type of question that I'd like to do with you. A little unique, a little bit strange, if you will. It's a rice question, KC calculation, that's a little out of the ordinary. Stay tuned, it's coming up later in the video. Let's take a look at this one. So carbon reacts with sulfur according to the following balanced equation. The system reaches equilibrium at temperature T in a sealed 2 dm cubed container. The Kc value is 9,4 at temperature T. We'll leave out the definition for Le Chatelier's principle. We'll jump straight into some of the questions. So at equilibrium, 1 mole of carbon disulfide is present in the container. Calculate the concentration of sulfur gas present at equilibrium. Pretty straightforward here. We'll start off with our Kc formula. So Kc expression is going to be the concentration of my products, which is CS2 in this case, divided by reactant, which is going to be S, and then to the power of 2. Careful here, we're going to ignore carbon because it's a solid. Now we'll substitute. We know that the Kc value is 9,4. That's equal to CS2. We've been given the number of moles and we know the volume. The volume is 2 and we know the number of moles is 1. So we can calculate the concentration, number of moles divided by volume. So 1 divided by 2 and then divided by S squared. So S is what we want, remember? So it's going to be concentration of S squared. We then solve for the concentration of S. That's going to be a half divided by 9,4, and don't forget to square root that. And that's going to give me an answer of 0,23 moles per dm cubed. Okay, the next question reads, the volume of the container is now doubled at temperature T, after a while a new equilibrium is established. How will the amount of S gas change as this new equilibrium is established? And then explain your answer in terms of Le Chatelier's principle. So we'll combine these questions just to make it a bit easier for us to answer. So 6.3 and then 6.4. If the volume doubles, so volume increases, that's going to have an effect on the pressure. The pressure will decrease. According to Le Chatelier's principle, the system will want to increase the pressure. And it does this by favoring the side with more molecules. So more molecules favored. Now if we look at our reaction, the left-hand side has 2 molecules, the right-hand side has 1 molecule. So the reverse reaction will be favored. And what does that mean in terms of the amount of sulfur gas? The amount of sulfur gas will increase. Now let's take a look at question 6.5. It reads, if the concentration of CS2 gas changes by X moles per dm cubed, write an expression for the equilibrium constant Kc in terms of X. Show all your workings. All right, so what we'll do here is we'll construct our rice table. So rice table looks like this. We're going to have 2S gas going to CS2 gas, RICE. Now, ratio, R for ratio, so the ratio is 2 to 1. Initial amount. Now, this is going to be a concentration table. Now, we have to be careful. The initial amount would have been 0,23, because remember, that was the amount at the previous equilibrium. But since the volume doubled, volume and concentration are inversely related. So if the concentration doubled, so if the volume doubled, the concentration would have halved. So the new initial concentration is going to be half of 0,23, which is 0,115. Okay? And then likewise, for CS2, it was a half a mole per dm cubed. Now it's going to be 0,25 moles per dm cubed. Okay? Now they tell us that the concentration of CS2 changes by x moles per dm cubed. So this is going to be x, but we answered the previous question, which said that the amount of sulfur gas will increase. So this side is going to be a plus. That means this side is going to be minus. Now, normally, the products would increase, the reactants would decrease. But in this scenario, because there was a change, the reverse reaction is actually favored, which means that you're going to have a plus on the left-hand side. Okay, now we use our ratio here. If that's 2 to 1, then this is going to be 2x. Now at equilibrium, we're going to have 0,115 plus 2x, and then here 0,25 minus x. Now we can set out our Kc expression. Remember, the volume was changed, which means that the Kc is going to be the same. So Kc is 9,4. That's going to equal the concentration of CS2. So 0,25 minus x divided by 0,115 plus 2x and to the power of 2. That's it. No need to simplify. That's our answer. And let's move on to this graph question. So the reaction rate time graph below represents further changes made to the equilibrium mixture. The volume of the gas is the volume of the container is kept constant. Okay. Fine. What do the parallel lines between TA and TB mean? It just means that the rates are equal. Right? So the rate of the forward equals the rate of the reverse. In other words, equilibrium reached. Right, so question 6.6.2 reads, what change was made to the equilibrium mixture? So they're asking about the mixture at TB. So when they speak about the mixture, something would have increased or something would have decreased. Now, we can clearly see from our graph that both rates increased, right? But the forward increased more, which tells us, so 6.6.2, that the forward reaction was favored. Now, what could they have done to the mixture to favor the forward reaction? If they added if they increase the concentration of sulfur. So if you increase the concentration of sulfur, the system will want to decrease the concentration of sulfur. It's going to favor the forward reaction, and there you're going to find the rates increasing. Okay? Question 6.6.3. Give a reason for the sudden change in the reaction rate at TC. So what we can see here at TC, both rates decreased, but one decreased less. So if I'm looking at it, I can see that the reverse reaction decreased less. Now what does that mean? So reverse decreased less. That means that the reverse reaction was favored. Okay, now let's look at our delta H for this reaction. If we increased the temperature, right, the rates would increase. Remember, increase the temperature, particles have more kinetic energy and more effective collisions per unit time, etc. But if we decrease the temperature, let's look at what would happen. A decrease in temperature favors exothermic, right? And if the forward is endo, it means that the reverse is exo. So if we decrease the temperature, the reverse reaction would have been favored. So that directly matches up with what we find in our graph. So the answer to this question, 6.6.4, so that we're saying the temperature decreased. And why? Why would this be a valid reason? Because a decrease in temperature favors the exothermic reaction. The reverse reaction is exothermic. That means the reverse was favored. That's it. Thanks so much for watching. I'll see you in the next one.